The goal of this workshop then is to provide tips and troubleshooting for people that are going to be doing immunoblotting or Western blotting. So that hopefully you and your group can generate clear and clean and publishable, hopefully quantitative, that's the spin on it that I really like to do, immunoblots. And not everybody currently does that, but I think it's very, very doable. And that's why I put this particular slide up here. This blot was performed by a third-year undergraduate student just this spring in a molecular biology hands-on course that I teach. And this was the first immunoblot the student had ever run. And what she's doing here is a quantitative immunoblot of D1 protein, photosystem 2, in a highlight treatment of Synechococcus. So hopefully the goal of this workshop is to have people generating blots that look something like this, or like this one, which was performed by my another third-year undergraduate student. That's a quantitative blot of ATPB, the beta subunit of ATP synthase in Seneca cystis. And this, again, one of the first blots that she's ever done. So the goal is to get blots looking like this. So how do we do that? So these are the points to consider, and I'm going to go through every one of these points in some considerable detail. Of course, I think it all rests on careful sample harvesting. And of course, before careful sample harvesting, you have careful experimental planning that went into generating those samples. But I'm going to take it from the sample harvest point. Really important to get everything cold very quickly. It's very important once you've got sample harvested to get a very consistent and a very efficient protein extraction from those samples. Because if you're only getting 70% of protein extracted from one sample and 90% from another, that's going to lead to significant variation, and you're not going to get good quantitative results. In order to get fully quantitative results, you need quantitation standards on your blots, and I'll talk a little bit about that. It's important to have a really good, consistent electrophoretic separation technique. There are many, many out there. The one that Natalie was performing earlier here is the one that I use because, again, I'm working with undergraduate students and it has to be of very high quality, very foolproof. And that's the Invitrogen new page system. So for separation, we're looking at a 4 to 12% new page gel. I'll go over that in detail in a minute. Once you've got separation, you really have to get quantitative transfer. So again, you have to pick your transfer method a little bit carefully. I've used quite a number of different ones. I use the wet transfer from Invitrogen. I'm not sold on their iBlot, which I don't think is as quantitative. They tell me it is, but in my hands it's not. Once you've got your protein onto a membrane, then you have to get appropriately diluted antibodies. That's very important to get quantitative detections especially. And then select some kind of reagent for detection. If you want a quantitative approach, you've really got to have a good image capture system. And then you have to do some sort of quantitation on it. So when it comes to sample harvesting, I can't stress enough that speed is of the essence. The minute you take your sample from its home environment, in this case, of course, trying to be very Canadian, I put a maple leaf up there. Take it off the plant, or in our case, it's usually working with algae, so we're spinning them down or filtering them. From the point of harvest, it's really important that you get that cold very, very quickly. So what we would typically do with plant samples would be to weigh them, note the weight, and immediately fold it up in tin foil and put it into liquid nitrogen very, very quickly. So everything is going to be flash frozen in liquid nitrogen to stop degradation of proteins, because as soon as the plant or the algae is dead, it's gonna degrade really quickly. Long-term storage must be at -80. -20 will not hold the proteins stable. It leads to degradation of proteins. You'll see bands below your main band on the gel, and you end up sometimes with them aggregating, not simply degrading. So it generally leads to them looking crappy if you store them at too high a temperature. For phytoplankton, I'll just point out here, there's two ways you can do it. You can spin them down in a centrifuge at an appropriate speed, depends on your organism, and pour off the supernate and pour off the media, or you can filter them onto binder-free glass fiber filters and then snap freeze them. All right, extracting the samples. there, and we've tested a number of them when we keep going back to test new methods. Our sort of gold standard protein extraction method is to take the tissue. If it's a plant tissue, we grind it in a mortar and pestle that has been pre-cooled in liquid nitrogen. You can see it's all fuming and frothing there. So a very, very cold mortar and pestle. We put liquid nitrogen in it. We put our leaf that's frozen in there, and we grind it to a fine powder. Okay, I don't do this step for phytoplankton, but we do this for any leafy root or roots or whatever that you're looking at. Once it's ground, we're going to put it into a tube. Here it's shown going into a small Eppendorf tube, often better off in a 15 mil Falcon tube. And then we're going to add some extraction buffer to the sample. The key component is LDS, that's lithium dodecyl sulfate, as opposed to sodium dodecyl sulfate. Other than just being more expensive, LDS is not as temperature sensitive, so it doesn't tend to precipitate out at low temperature like sodium dodecyl sulfate does. It gives a slightly sharper band on a gel. There's other buffers in there. It has some glycerol for density, for loading, but the LDS is the key component. So what we do is we take, say, 500 microliters of our 1X sample buffer, to which we have added protease inhibitors, not DTT, however, at this point. Important distinction there. Don't add any reducing agent at this step, but do add protease inhibitors. I have not systematically tested them, and I can't tell you which one is better than others. I use Pefablock from Roche, but I think that there's lots of possibilities out there for protease inhibitors. So what you're going to do then is you're going to end up with your buffer on your sample and flash freeze it in liquid nitrogen vertically. So you've got frozen, say 500 microliters, 300 microliters of sample buffer in a tube. The taller the tube, the better, but small tubes can work as well. The reason I say to flash freeze it vertically is that it's at the bottom of the tube and it doesn't fly all over the place. Because what we're going to do to break the tissue, break the cells open, is to sonicate with a micro tip at about 30% of the maximum output. And what we do here is a method that we call soni-thaw, where we take the tube straight from the liquid nitrogen and apply the tip to the end of it and kind of grind away at it with the sonicator just until it thaws. Just before it thaws, it goes to a stage that looks just like a lime slushy, green and slushy, and then it goes to liquid. You stop by the time it gets to liquid. If you go any farther, you'll get like a bubbly mess, and that's very bad. So stop as soon as you thaw, and then I refreeze vertically, and I do 3 soni-thaw procedures for each sample. It depends a little bit on the sample. Most leafy plant tissues don't need a full 3 goes. Something like spinach, 1 or 2 goes is enough. Some of the crunchier little Synechococcus, I have to really go at them at least 3 times. Diatoms are also very crunchy and a little hard to break open, but you have to use your judgment a little bit. The way to test it is when you're done, your third sonication or your final sonication, you don't refreeze, you centrifuge. So transfer it to a 1.5 mil Eppendorf and centrifuge at full speed for 5 minutes, 3 to 5 minutes. Cool would be best, room temperature is fine, and that's what we do most of the time. This is the point where you have to use a bit of judgment. You look at the sample. If the pellet is greener than the supernatant, you need to keep going with the sonication. If the pellet is the same amount of green as the supernatant, you're good to go. Take the supernatant off to a new tube, and that's your protein extract. Once you have an extract, it's going to be anywhere from pale yellow, probably maybe even brown if you're talking roots, to quite dark green. You have to load your gel based on some parameter. Some people use leaf area or wet weight. We tend to use total protein loads. So what we're going to do is take the extract and do a protein assay on it. Now there's different methods you can use, but the one we found that works the best with the amount of detergent in these samples is a Biorad DC assay. And that's the reason we haven't added the DTT yet, is because that assay is finicky, it doesn't take DTT. So we do a Biorad DC assay. I use a microplate assay usually, doesn't use very much of your sample, and can be done in triplicate quite quickly. When I talk about on this slide about the loads that you're going to use, this is if you have a very sensitive detection method. I generally load 1 microgram of total protein, which is not a lot. Some people load 10, 100 times. I've even heard of almost 1,000 times as much. It's very hard to get quantitative immunoblots with that, but sometimes with a less sensitive detection method, you might get pretty blots with that. But for quantitative immunoblotting, you want a consistent protein load and you want quite a low protein load. And I'll talk about why in a minute. So generally, I load a microgram of total protein. And I say here that it's in even volumes, and this came up in the little demonstration beforehand. If you load 1 microliter of one sample and 12 microliters of the next one, the one that's 1 microliter tends to run as a little ball instead of a nice band. So what I do is I make up every sample being 1/10 volume DTT, so that's 50 millimolar final, so it's a 10th volume of 0.5 molar, and then my sample, and then the rest is just 1x sample buffer. I use the blue new page sample buffer from Invitrogen because that makes every sample blue and it's really easy to see when you've loaded it. If you use a clear sample buffer, that way madness lies, but you can do it. But the blue makes it easy to see. So I've made everything up to say 10 or 15 microliters, and then I load a constant volume. So the key to good Western blots, of course, is to have a good gel separation. There's lots of systems that will do it. We use the new page system. It's not cheap. They're $20 a gel, but they're very, very consistent. Time is important when it comes to the gels. For smaller proteins, obviously shorter period of time, larger period of time for larger proteins. If you want a very pretty gel, cool your running buffer overnight at 4 degrees. It keeps it cold. And as I said during the demonstration, it's important to not be stingy with the bottom, the outer chamber, to have that come up quite high up the gel because its main purpose there is just to cool the gel. And so the colder you start with it, the better the gel is going to run. So once you've got good separation, you're going to transfer to a membrane. Your choices, of course, largely PVDF or nitrocellulose. We use both. I'm a fan of PVDF because everything I did early on was on hydrophobic proteins, so PVDF is the membrane of choice for hydrophobics. For hydrophilic proteins, nitrocellulose is fine as well. The key here, this transfer step, is about quantitative transfer, as we sort of spoke about earlier. I always run 2 molecular weight ladders on every gel. I mix them together. I run a pre-stain. In this case, we're running Novex Sharp. Can be Precision Plus from Biorad, any of those pre-stain markers. And to that, I add some IgG tagged marker. So the one I use is Magic Mark from Invitrogen. You only need about 1/2 microliter of that. And that way, we're going to see sizes on the final immunoblot, but we're also going to see migration as it's happening right now. You'll see the protein, the pre-stains separating, and we're going to be able to see how efficient the transfer is. So I sort of insisted on every gel you have colored marker, because when you transfer, if you see any protein left behind in the marker, guaranteed proteins left behind in the gel. If you're wondersome about it, if you're troubleshooting your transfer technique, it's important to stain the gel after transfer. You can stain it in something as simple as a Kumasi, or you could put it in silver stain just to see. And what you'll probably see is that it's completely transferred at the bottom and less so towards the top of the gel. And it depends on what size of protein you're looking at. The standard protocol that we use uses the new page transfer buffer as it's stated in the manual, and we use 80 minutes at 30 volts for 2 gels and 60 minutes at 30 volt for 1 gel. Smaller proteins, I do less time because they tend to zip right through the membrane if you're not careful. You can test that as well, troubleshoot that by putting a second membrane on top of the gel and see if anything comes through onto the second membrane. So when you're getting your own system set up and you're troubleshooting, important to put ladder, important to stain the gel to see if you've got complete transfer, or if it's patchy. Because some of the problems with the dry systems is they get patchy, places that don't get good transfer if they don't have good contact or you haven't really rolled the bubbles out well, and then you lose information.